Okay, guys, our last piece that we have to move into our rotational domain is our conservation of momentum. So with that, what we are going to be looking at today is our example problem, which is looking at a record. So we have hopefully something circular-ish there. A little record seat going around. We got the title and everything in the middle. We have this guy spinning, and it is spinning at a total of 45 RPM. And it has a radius of 0.2 meters and a mass of 0.2 kilograms. And what we're going to do to it is we're going to be terrible guests, and we are going to go ahead and stick a cup on it. So we set our drinking glass on it. We set it a distance from the center of 0.1 meters, and it has a mass of 0.5 kilograms. Perfect. And with this, what we're going to do is we are going to figure out how it slows this down. So technically in a real record system, what's going to be happening is there's some force that's actually turning it. In this case, we're just pretending we've got this freely spinning, infinitely spinning record, no friction or anything going on it, and we're setting a glass down and seeing what happens to that glass. So what we want to find, we want to find the omega, we'll call it at time 2, the rotational rate at time 2, rotational velocity, and we want to find the difference in the period of one versus the other. So how long, so period being how long it takes to go in a full circle, how much has that changed? So with that, we're going to do a couple of side quests first. First thing, we have RPM, and RPM is not an equation piece. So with this, well, we could use it in this case, but we shouldn't. Bad practice. So we have 45 rotations in a minute, and we want that in a omega term, so we want in radians per second rotations. One rotation is 2 pi radians, and 1 minute is 60 seconds. This gives me a rotational rate of 4.71 radians per second. So 4.71 radians per second. Okay, that guy worked out perfectly. Second thing we're going to need is we're going to need our moments of inertia for everything going on here. So with that, we can start with our initial record. So at the very beginning, our record is just spinning. It is going to act as a disk. So 1/2 mr squared. We have all the values for this. So 1/2, my mass of my record is 0.2 kilograms. My radius is 0.2 meters. That is squared. That gives me a value of 0.004 kilogram meter squared. Then I have my glass, which is being added. That is going to act as a point mass, so that is going to be just straight up mr squared. So that is, my glass has a mass of 0.5 kilograms, and my radius is 0.1 meters. That squared is going to give me 0.004 5 kilogram meter squared. Great. And that means that I can now find my final rotation rate. So not final rotation, my final inertia. So total inertia. So initially it's just the record. Afterwards it's both of these. And our inertias are going to add up. So it's going to be I of the glass plus I of the record, which is going to be 0.005 plus 0.004. So 0.009 kilogram meter squared. Perfect. Okay. That is all the background stuff that I'm going to need to know. Now I can throw it into my momentum equation. So my momentum equation, which used to be mv, is now I omega. So at time 1, I've got I1 and omega 1. At time 2, I've got I2 and omega 2. So in this case, my initial I is my I of just the record, which is 0.004 kilogram meter squared. My initial omega, we just solved for as 4.71 radians per second. And that is going to be equal to my I2, which is my total, which is, because time 2 I have the glass sitting on it, so 0.009 kilogram meter squared times omega 2. And with that, I can solve for omega 2. Omega 2 is going to be 0.004 times 4.71 divided by 0.009 kilogram meter squared. Cancel, I get radians per second. And that gives me a total rotational rate of 2.09 radians per second. So the omega 2 is 2.09 radians per second. Great. Next thing I have to do is convert these guys, try to get that decimal point to show up, convert these guys into periods. So currently I have rotational rate, which is radians per second. Period is seconds per cycle. So with that, we'll erase the top bit and work up top. So I've got to find the period for each of them. The period for the first one, so we'll call it the initial state. So I am after t, so in t1, in order to get that, I'm going to start by writing my omega 1, but I'm going to write it upside down. So I'm going to have 4.71 radians per second. I can convert radians into cycles or revolutions, because 2 pi radians is 1 cycle. So I can go ahead and solve that. And I have seconds per cycle. It takes 1.3 repeated seconds for the disk to go, for the record to go around a full revolution initially. And in my final state, it's the same thing, T2. I'm going to go ahead and write my 2.09 upside down now, 2.09 radians per second. I've got 2 pi radians per cycle. That comes out to 3 seconds. So the difference is going to be 3 seconds minus 1.3 repeated seconds which is 1 2/3 seconds is the difference in how much slower it is. So it originally took 1 1/3, it now takes 3 seconds. That's 1 2/3 seconds longer. Nothing crazy going on there, but that is our momentum example problem.